Hi everyone, I'm Jessica Deen. Welcome to DapRCon. Today we're going to be talking about key considerations for running Dapr in production. We will start by reviewing the landscape of microservice development and what problems Dapr solves. Then we will cover key considerations for running and using Dapr in production with Kubernetes. And at the end, we'll walk through some next steps and provide resources to get involved with the Dapr community and learn even more. Let's start with a brief overview of microservice development and how Dapr simplifies this for us. No matter what industry we're in, writing software has common patterns. We reduce costs by only using the resources we need and scaling out when additional resources are required. Applications are being broken down into units of functionality, each exposed as a service. We want to focus on adding business value and not managing infrastructure. So we leverage serverless platforms and use DevOps best practices. And the number of programming languages seems to never stop growing, and we should always use the best language for the task at hand. On the surface, microservice development seems simple enough. It's a micro or small service and not a giant scary monolith. However, there are limited tools and runtimes to support truly distributed development. And many of the frameworks are tightly coupled to a specific language or development stack. A typical microservice application might look like this: several small, purpose-built services all talking to each other. Some of the services also talk to external resources to store state or ingest events. Getting an application like this up and running and keeping it running has proven to be challenging. At its core, Dapr is a set of building blocks, including service-to-service invocation, state management, pub/sub, bindings, and secrets management, with support for the actor model and observability right out of the box. We can use as much or as little as we like. For example, if we have already solved service-to-service invocation, but need help with state management, we can just use the state management building block. Or if we're starting from nothing, we can use it all, allowing us to focus on what matters, adding business value. Any language that can send an HTTP or gRPC request can use these building blocks. This is one of the reasons Dapr is so powerful. Not only can applications that leverage Dapr use any language, they can be run on any infrastructure. The components are the real magic behind Dapr. Switching from Redis to Cosmos DB or from RabbitMQ to Azure Service Bus requires zero code changes. We simply update our configuration and the code gets to stay the same. If we do not see a component we need, no problem. They're all open source and we can add whatever we need by simply submitting a pull request. The goals are to take years of experience and best practices and make them easy to use for any language and on any stack. Dapr is driven by standards and provides a consistent, portable, and open API that can be extended and used in any cloud and on the edge. It was developed by the cloud-native community as a way to ease distributed application development. To recap, Dapr offers best practice building blocks, consistent, portable, and open APIs, extensible and pluggable components. It supports any language or framework, it's platform agnostic, and it's community-driven and completely vendor-neutral. Now that we understand microservice development challenges and Dapr's goals better, let us shift our focus to deploying Dapr in production. There are 5 Dapr control plane deployments: operator, sidecar injector, sentry, placement, and dashboard. When deploying Dapr in a production-ready configuration, it's recommended to deploy with a highly available configuration of the Dapr control plane. A highly available configuration will create 3 replicas of each Dapr control plane pod in the Dapr system namespace. And it allows the Dapr control plane to survive Kubernetes node failures and other outages. When using Dapr in production with Kubernetes, you should also run a Kubernetes cluster of at least 3 worker nodes to support a highly available installation, with the Dapr control plane resource requests and limits also defined. While resource settings requirements will vary depending on cluster size, The resource request and limits table here shows a good starting point, though individual testing will be needed to find the right values for your environment. You can install Dapr one of three ways. First, you can use the Dapr CLI. This is the recommended way to get started with Dapr. Second, if you prefer, you can use Helm. If you choose to use Helm, it's recommended to create a values file instead of specifying parameters on the command line. This file should be checked into source control so you can track changes made to it. It's important to note the latest Dapr Helm chart no longer supports Helm version 2. You will need to migrate from Helm version 2 to Helm version 3 if you wish to use this installation method. Third, if you're using Dapr in production properly, you will have continuous integration and continuous delivery configured for your application delivery. If you're familiar with GitHub Actions and are using it for your CI/CD, Dapr can be integrated with GitHub Actions via the Dapr tool installer, available right in the GitHub Marketplace. This installer adds the Dapr CLI to your workflow, allowing you to deploy, manage, and upgrade Dapr across your environments. Here are examples of the 3 different ways to install and deploy Dapr. You can see using the Dapr CLI is the easiest, as it's one line of code. Helm requires a few extra steps, but you can check in your configuration to source control, thus allowing you to track configuration changes. Finally, with GitHub Actions, there is a native step allowing you to set up Dapr on your GitHub Actions runner, thereby providing access to the Dapr CLI. The Dapr Setup Dapr action will install the specified version of the Dapr CLI on macOS, Linux, and Windows runners. Once installed, you can run any Dapr CLI command to manage your Dapr environments. Notice both the Dapr CLI and Helm examples use a flag to enable high availability for Dapr. Like installing Dapr, you can use the Dapr CLI or Helm to upgrade Dapr in Kubernetes. It also supports zero downtime upgrades. The upgrade path looks a little like this. First, update the CLI version. This is optional, but recommended, as this will upgrade the CLI for the client. This can be your workstation or your CI server or runner. Second, update the Dapr control plane itself. This is what is deployed in the Dapr system namespace and is made up of those 5 deployments we spoke of earlier. Third, update the data plane. These are the Dapr sidecars deployed right alongside your app. Again, here are 2 examples of what an upgrade command would look like whether you're using Dapr CLI or Helm. As you can see, the Dapr CLI is still only one line to upgrade the runtime version in a Kubernetes cluster, whereas the Helm command is a few more. Again, regardless of which method used, Dapr CLI or Helm, after the upgrade of the Dapr control plane, you will have to update the data plane, which will upgrade the Dapr sidecars for your application. The Helm example shows a kube control rollout restart command to demonstrate this. What I'd like to do now is go into a demo of upgrading Dapr with truly zero downtime. Let's check it out. When running code in production, updating anything server-side and customer-facing can be a little daunting. It can be a little scary, right? Luckily with Dapr, when you have to update from one version of Dapr to the next, you can do so with zero downtime. Let's take a look. If we run a Dapr status -k command in our terminal, we can see in the version column we are currently using 1.4.0. I can also run a kget deploy command to see the deployments I currently have running in my production Kubernetes cluster in this particular namespace called Twitter Sentiment. You can see we have 3 services running, each with 3 replicas, and then we have Zipkin, which is tracing given to us by default thanks to Dapr. We'll learn more about tracing later today. These 3 services all run a Twitter Sentiment Daprized app, which ingests tweets based on a query string and then grades the sentiment using Azure Cognitive Services. Best of all, Dapr made wiring up the Twitter bindings and authentication super easy. But since this is a Daprized app, and it is currently running in my production Kubernetes cluster, I need to be confident there will be zero downtime if I move from 1.4.0 to the current release of 1.4.2. Let's test this out. I'm going to split my view here, and in the bottom pane, I'll run a watch command on the Dapr system namespace so we can watch the upgrade in real time. In the top pane, let's run the Dapr upgrade command. You'll notice I'm using -k, and that's because we're using Dapr with Kubernetes. I'll follow that up with the runtime version flag, where I can specify a specific version I want to upgrade to. We're going to move from 1.4.0 to 1.4.2, which is the latest version of Dapr as of this demo. I'll hit enter, and that's it. Dapr will start upgrading the control plane, and I'll bring up our Twitter sentiment app side by side so you can watch the upgrade happening in real time with zero downtime. Now, we do see some warnings here in the background that tells us there will be some changes to how Kubernetes handles pod disruption budgets in future releases of Kubernetes. Those are just informational messages, not error messages, so we can disregard and let Dapr complete the rolling upgrade. You will notice, though, as Dapr does its upgrade thing, we are still getting tweets. We're still able to grade the sentiment, and we can even take a quick look at Zipkin and run a query. Remember, Zipkin is provided to us with no extra effort thanks to Dapr. We can still do traces with Zipkin, despite Dapr's ongoing rolling upgrade in the background. We'll flip back over to our actual app and watch our tweets come in as the Dapr control plane continues to upgrade. And there we go. The Dapr control plane has been successfully upgraded to Dapr version 1.4.2, and the entire time the upgrade was happening, we didn't have any downtime for our application itself. Let's perform a quick sanity check to ensure we are now, for real, on the 1.4.2 version. We'll run Dapr status-k, and you can see in our version column, we now have updated to exactly what we'd expect, 1.4.2. Fantastic. All right. Now that we have covered installing and upgrading Dapr in production, let's move on to security. Dapr supports in-transit encryption of communication between Dapr instances using Sentry, a central certificate authority. Here's an example application with two services, Service A and Service B. Thanks to Dapr, all communication between services A and B is done so securely using mutual authentication or mTLS. Dapr is implemented using the common sidecar pattern where a second process runs alongside our main process. The main application uses HTTP or gRPC requests to call into the Dapr sidecar to take advantage of the desired building block, and the sidecar instances securely communicate with one another, as we can see here. Now, why is this so important? I'm so glad you asked. mTLS offers a few key features for network traffic inside your application. First, it offers two-way authentication, the client proving its identity to the server and vice versa. And second, it offers an encrypted channel for all in-flight communication after two-way authentication is established. With Dapr, there isn't any extra work needed to get this up and running. Dapr includes an on-by-default automatic mutual TLS that provides this in-transit encryption for traffic between Dapr sidecars. It also manages workload and certificate rotation. It does so with zero downtime to the application. You can even bring your own certificates. If custom certificates have not been provided, no worries. Dapr will automatically create and persist self-signed certs valid for 1 year. In Kubernetes, the certs are persisted to a secret that resides in the namespace of the Dapr system pods, making it accessible only to them. This slide shows how the Sentry system service issues certificates for applications based on the root issuer certificate that is provided by an operator or generated by the Sentry service and stored as a Kubernetes secret object. mTLS settings for Dapr reside in a configuration file. Here you can see all the available settings for mTLS in a configuration resource object. By default, a workload cert is valid for 24 hours and the clock skew is set to 15 minutes, though you can change this as needed. What I'd like to do now is jump into a short demo where we show you how granular you can get with your mTLS settings configuration. Let's check it out. Do you like SSL? Would you say you love SSL? You should love SSL. SSL makes your life secure. I like SSL, but maintaining it can be an absolute pain. Maintaining SSL means ensuring your SSL does not expire and ensures it's properly implemented. Now, would you say you love mutual SSL? Probably not. It can be an even larger headache since mutual SSL, otherwise known as mTLS, doubles your burden because the same thing has to be implemented in two places. It's a mutual exchange between two services where both services are assured of the other's identity. Lucky for us, Dapr takes care of all of that by default. Dapr supports in-transit encryption of communication between Dapr instances using Sentry as your central certificate authority. If you'd like, you can bring your own certificates or allow Dapr to automatically create and persist self-signed root and issuer certs for you. To confirm mTLS is enabled on your Kubernetes cluster with Dapr support, simply run the Dapr mTLS-K command. You should see confirmation mutual TLS is enabled, which it should be unless you explicitly disabled it when initializing Dapr. mTLS settings reside in a Dapr configuration file, which in turn creates a Dapr configuration resource object. The default settings are 24 hours for clock skew and 15 minutes for time to live, but you can change those based on your needs or desires. Example, let's update ours here to 5 seconds for clock skew and 15 seconds for our time to live. This means Dapr will rotate our mTLS certificates every 15 seconds without any interaction from us as developers or operators. Now, of course, in production, you wouldn't want to edit any configuration on the production cluster. You'll define it in your infrastructure as code during deployment. But this is a demo to show you specifically how the certificate rotation works with Dapr. Any changes made to the Dapr control plane will require a restart to that control plane. We can do that using a rollout restart command. I'll do that here in my top pane and hit enter. In my bottom pane, I'll run a watch Dapr status command so we can see when everything is healthy again. Remember, as we saw in our zero downtime video, any changes made to our control plane will not affect our Daprized apps running. Great. Now that the control plane has been restarted with the configuration changes, we'll stop the watch command and perform a rolling restart of our Twitter sentiment app so it can pick up the updated Dapr sidecars with the new configuration. We'll again do a watch command on this rolling update to ensure the restart is complete for our Twitter sentiment app. Excellent. Now let's take a look at the logs for any one of our services. I'll go ahead and choose viewer, for example, and I'll add the follow flag to the command so we can watch as the certs roll every 15 seconds. Again, this is all thanks to Dapr for making SSL easier than ever before. When properly configured, Dapr ensures secure communication. We've already touched on mTLS and we've seen it in action, but let's focus on some other settings a production-ready deployment should include. In addition to mTLS, there is app-to-Dapr API authentication. This is the communication between your application and the Dapr sidecar. To secure the Dapr API from unauthorized access, you can enable Dapr's token-based authentication. Dapr uses JSON Web Tokens, or JWTs. In order to configure this, you would generate your token using any JWT token-compatible tool and then create a secret object in Kubernetes with that token. Dapr will then leverage the secret store in Kubernetes to hold the token, which can then be referenced in your deployment using a simple annotation. In this example, the annotation is API token secret with a value of Dapr API token. Finally, there is Dapr to app API authentication, which is the communication between Dapr and your app. This ensures Dapr knows it's communicating with an authorized app. Similar to app to Dapr auth, this also uses a JWT token, and again can be referenced using a simple annotation. Note, there are two annotation examples here. One is API token secret, and the other is app token secret. To recap, app to Dapr auth secures the Dapr API from unauthorized application access, whereas Dapr to app auth ensures that Dapr knows it's communicating with an authorized application. A production-ready deployment should include both of these authentication configurations. Now let's talk about namespaces. When running Dapr in production, there are three primary factors to consider. First, the Dapr control plane should be installed in a dedicated Kubernetes namespace. By default, it's installed into the Dapr system namespace, so this works great. Second, while not a technically required practice, it's important to note Dapr supports scoping components for your apps. This can and should be enabled according to your security needs. You can see in the example under metadata, we have scoped the Redis state store component to the production namespace. An alternate example is if you're using Helm and you want to scope it to the release namespace for your Helm chart. Finally, you will want to consider your service invocation. When using service invocation with a Daprized app in a namespace, you will have to qualify it with that namespace. In this example, we're referencing the Zipkin endpoint address with a qualifying namespace depending on where the Zipkin tracing component has been deployed. If we use the production namespace we saw in the Redis component on our previous slide, this Zipkin address would read http zipkin.production.svc.cluster.local, etc. Moving on, let's also highlight secrets and how to securely consume secrets in production using Dapr. Secrets management gives us a consistent way to access connection strings, keys, passwords, and other sensitive information in our application. We've discussed the importance of considering namespaces when using Dapr in production. It's important to remember this when your components need to fetch secrets. When running in Kubernetes, Dapr, during installation, defines default role and role binding for secrets access from the Kubernetes secret store in the default namespace. For Dapr-enabled apps that fetch secrets from the default namespace, a secret can be defined and referenced in components. However, in a production scenario, you will deploy your apps and Dapr components to non-default namespaces. If those Dapr-enabled apps are using components that fetch secrets from non-default namespaces, for example, Twitter Sentiment, which is the namespace we have used for our sample app, you'll need to configure the proper role and role binding for that namespace. This slide shows an example of the resource configuration. Note, two separate resource objects are being created. One is role, which is the secret reader. It is scoped to the secret resource with get and list permissions. The second is role binding, which is the Dapr secret reader, scoped to a service account referencing the secret reader role. These resources grant Dapr permissions to get secrets from the Kubernetes secret store for the namespace defined in the role and role binding. While you have the option to use plain text secrets, like my password as shown in the YAML on the left for the value of the Redis password, this is not recommended for production. Dapr natively supports a wide variety of secret stores, including Azure Key Vault, GCP Secret Manager, AWS Secrets Manager, HashiCorp Vault, and more. Components can reference secrets for the spec metadata section within the component's definition. In order to reference a secret, let's look at the example on the right. You need to set the auth secret store field to specify the name of the secret store that holds the secrets. But if that field is empty, that's okay. The default secret store will be used. Let's now jump into a short demo showing the proper way to configure secrets with Dapr. Let's talk about secrets. It's common for applications to store sensitive information, such as connection strings, keys, and tokens, that are used to authenticate with databases, services, external systems, and APIs in secrets by using a dedicated secret store. Usually, this involves setting up a secret store, such as Azure Key Vault, HashiCorp Vault, or something similar, and then storing the application-level secrets there. To access these secret stores, the application then needs to import the secret store's SDK. This may require a fair amount of boilerplate code that is not related to the actual business domain of the app, and so becomes an even greater challenge in multi-cloud scenarios where different vendor-specific secret stores may be used. This is where Dapr comes in. In an effort to make life easier for devs, Dapr has a dedicated secrets building block API that allows you to get secrets from a secret store. Take our Twitter Sentiment app, for example. There are a lot of secrets we need to store for this app to work. Remove the vendor-specific secrets like connection strings to storage accounts and Azure Cognitive Services. We need secrets to authenticate with the Twitter API. We connect our app to the Twitter API through a Twitter binding component, where we pass 4 required secret parameters: our consumer key, consumer secret, access token, and access secret. We can take a look at how that binding is currently configured, where we have simply passed values to our deployment and then performed a base 64 encryption on it. While this certainly works, it's not really secure and it doesn't utilize secret storage, which would be the appropriate way to address these secrets. To fix this, we can create a secret object in Kubernetes with this data, again, still encrypted. This will now be backed by whichever secret storage you have configured Dapr to use. In this case, we are simply using the Kubernetes secret store. Once you define your secret object, you will then reference those values in your Dapr component. We can do that easily with our Twitter bindings component by referencing the secret we just created and then subsequently the key for each secret. I'm going to save this and let's redeploy our app. Great, now that our app has been redeployed, we can again take a look at our Dapr tweets component, and this time we see our Twitter binding is using secrets stored in our secret storage instead of being passed directly. We can confirm the secret has been created by doing a kgetSecrets, demo-twitter-secret. That's what we named our secret object. And we see that secret has been created and contains 4 data entries, aka our 4 secrets. For posterity, we can bring up our app and verify, yep, we are still able to connect to Twitter and thus ingest and grade the sentiment of tweets. Only this time, we're doing it the right way with security in mind. Thanks, Dapr. The last thing I want to highlight is Dapr's tracing and metrics configuration. Observability gives us tracing across all the services in our application. With the Dapr, we can configure where we want the telemetry sent. This slide shows the same tracing information visualized from Azure Application Insights and Zipkin. Zipkin is a distributed tracing system. It helps gather timing data needed to troubleshoot latency problems in service architectures. Features include both the collection and lookup of this data. Best of all, Dapr supports Zipkin by default. This means that as a developer, we don't have to write any special code for this to work. Dapr also exposes a Prometheus metrics endpoint on port 9090 that you can scrape to gain a greater understanding of how Dapr is behaving and to set up alerts for specific conditions. You can view Dapr metrics using Azure Monitor, Grafana, New Relic, and, as already mentioned, Prometheus. It is recommended that you set up distributed tracing and metrics for your applications and the Dapr control plane when using Dapr in production. However, if you prefer your own observability setup, you're welcome to use that as well. Phew, we have been on quite a ride today. Thank you so much for hanging out with me. We've learned so much. Let's chat real quick about the resources you can use to get involved and continue your learning journey. The community momentum around Dapr is incredible. We released 1.0 in February, and it was submitted to the Cloud Native Cloud Computing Foundation in March. It's also great to see support from organizations around the world. Now, if you want to learn more about best practices, operations, security, and more, the best place to do so is our docs, available at docs.dapr.io. If you'd like to join the community, you can use any of these links to do so. You're also welcome to follow us on social media. And there's a great ebook available titled Dapr for .NET developers. Again, thank you so much for spending this time with me, and I can't wait to see you building incredible cloud-native applications with Dapr. Have a wonderful time at DaprCon. Cheers, y'all.